last time we stopped until the how to prepare and how to calculate your crude enzyme. Okay, so now we're going to move to the second part, which is the qualification. Okay, so what we have done last time, we have used one of the method, which is affinity chromatography. Okay, so I'm going to share the screen now. Okay, can you see the screen now? Someone please respond.
Yes,
Can.
brother.
So now we have this, what we have done last time. We have used affinity chromatography technique. So based on from the crude, so what happened, we just need to clean up or polish the protein. Okay, remember your crude, you have your metabolites, some of the DNAs, RNAs. Okay, so once you have prepared the crude, inside the crude you have your target protein, which is your enzyme, and then you have the impurities, and then you have the metabolite, and then also nucleic acid. So how do we separate all this? Because this material, they are all solid. This thing dissolve in the buffer. So it mix up with your target protein. How do we purify? How do we separate them from the crude? How do we separate our target protein from the crude is based on this technique, which is affinity chromatography we have used last time. So, okay, maybe before here, I will go to this one. Recombinant technique. Recombinant DNA technology. So basically, in your protein last time, in your DNA, in your crude protein, you have this called tag protein. Your protein now is being tagged by the affinity histidine. Okay, you're using histidine tag. So let's say if you have this, I need to make it bigger. So basically, in your gene, okay, you have the bacterial, you have the promoter here, then you have the operator, and then you have the boson binding site, and then you have the polylinker where you put your protein, your target gene, okay, your target gene. Okay, so in our case, we have used lipase. So that means the lipase DNA sequence, the lipase gene will be placed in this section, and then after that, once it start to the cell is induced with the IPTG, the promoter will be induced with the IPTG, and then that's the time where the transcription is initiated. Okay, the transcription initiated, and then it will transcribe your lipase gene. Okay, so now we have the mRNA of the lipase, and then we have at the C terminal. So remember, if this is the 5 prime, this one. Okay, this one will be your, I don't want this color. Okay, so okay, this side will be your 5 prime. Okay, and then this side will be your 3 prime. So this is your gene and then the mRNA. After that, you have the histidine. Histidine repeat at the, okay, 6 times his. Okay, we have 6 histidine at the back here. So that means your gene now is fused with this histidine tag. Okay, the histidine tag. Okay, so let me just draw like this. So you have your gene here, and then this is your N terminal. Once it is translated, then this side will be your N terminal, and then this side will be your C terminal. So your lipase gene now is fused. Okay, this side will be your lipase gene. Okay, this one will be your lipase. Okay, I should type it in. This side will be your lipase, and then this side will be your histidine. Histidine repeat. Histidine repeat. Okay. So from this histidine, oops. Okay, this histidine repeat basically will be the tag for your target protein. So because of this histidine repeat, that's why you can use the affinity chromatography. How do you guys stop this annotation? Okay, so that's why you can use this affinity chromatography. Okay, so it is not necessary your histidine. Okay, your histidine, it is not necessary to be at the C terminal. It also possible to be at the N terminal. Okay, it is not compulsory to be at the back. It is possible to have it at the N terminal. Okay, at the beginning. So now you have your target protein here. I mean your column here, equilibrated column, and then what happened? Okay, you can see that this is where you start to apply your sample. Then you can see the his tag protein. Okay, the tag protein will bind to this matrix, and then you can see the one without the tag, which is other than this blue balls. Okay, they just pass through and then eluted as the flow through. Okay, and then after that you start to apply different salt concentration. For this case, we use imidazole. Okay, imidazole will compete with the histidine tag here, and then it will just elute your target protein. This is where your target protein will be eluted. So why do we have only one band, one peak for this? This is because the protein that binds specifically to the matrix is only your target protein. So it will be, the thing that will be eluted is only the tag protein. So we need to make sure that the tag works well before we start using this technique. Works well meaning that you need to check using the Western blot. Okay, we need to do the Western blotting. Okay, let me just give you some little bit information about Western blotting. Western blot. Okay, so this is the Western blot example. Okay, so maybe this one is easier. Yeah. So basically, this Western blot. Okay. Okay, still bad, still slow. So I will just make it bigger for this one. Okay, so basically what is Western blot? It's just like you run this gel, which is your SDS, fish gel or native gel. Okay, when you run this gel, and then you will do the membrane transfer, meaning that your gel, your polyacrylamide gel will be transferred to a membrane. This membrane either you can use PVDF membrane or nylon membrane. Okay, so this membrane, whatever protein from this acrylamide gel. Okay, this is just, you just need to run the gel. You do not have to stain. Do not stain the gel. And then after running the gel, of course, there will be nothing can be seen. Okay, that's okay. So what happens next? You're going to transfer to this membrane. Okay, after you have transferred to this membrane, you can see that not you cannot see, but basically what happened during this transfer, all the bands, all the protein from this gel will be transferred to a membrane. Okay, so from this membrane, you will perform the blocking, and then after that, you're going to incubate with the primary antibody, and then a secondary antibody. Then after that, you go for the detection. Okay, so this detection, you can see that whatever protein bands, I mean protein in this SDS page, initially they are all in on the SDS page. Once it is when they are all transferred on the membrane, and then what happened during the Western blot, you can see only the protein band with the tag. I mean with the um, secondary antibody bind. Okay, it will give you the band. Okay, so if you compare with the normal SDS, you can see a lot of bands in the crude, right? So if you have 4,000 protein, and then there are hundreds of bands on the SDS page, basically when you run this Western blot, it will detect only the protein with this primary and secondary antibody bind to it. Okay, then you can visualize by during the detection technique. So if you can see the histidine tag, okay, so if you can see the histidine, okay, for example, if histidine present in here, when you run the Western blot, you can see protein band with the histidine. Okay, so it will give you some idea. Okay, so the, 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 the protein now is being tagged with the histidine, and then you can proceed with this affinity chromatography. Okay, if it is, if the Western blot shows nothing here, meaning that you shouldn't expect something will happen in this, because there will be no tag. Okay, there will be no tag. I mean, tag is not visible enough. Visible meaning that exposed enough to bind to the matrix. Okay, so basically before we proceed with this, sometimes we use this Western blot to check the presence of the tag. So the tag protein will be visualized in the Western blot. And then after that, we can purify using affinity chromatography. Okay, then it will be like, okay, the impurities will be eluted during the flow through, and then the pure protein, the target protein will be eluted in the elution. Okay, so now you are going to measure what is the activity here, what is the total activity that you get here. Okay, the amount of the protein plus the enzyme activity that you can get from here. Okay, so to evaluate or to assess either your purification techniques is okay or not, is acceptable or not, then you need to construct a purification table. So, the purification. Okay, so we have learned there are lots of we call it step for the purification. So we can see that for our case just now, since we have only one step, if we have only the affinity chromatography step, so our purification table will be, first will be the Maybe I will use yeah. Okay, so there will be only which one is clear? Okay, this one. I think this one clear. Can you see this clearly? This part?
Can, doctor.
Okay. Okay, so okay, clear. So we have the crude extract here. Okay, assume this is our first time we extracted the sample with the impurities. I mean, with all the metabolites, the nucleic acids and the impurities. So this is the total protein. So we stopped last time. We stopped until we have got unit per mil. Okay, we have got last time um, activity, X activity in unit per ml. Okay, so we have got unit per ml of activity, and then we have Y milligram per mil. Okay, so this one for for activity. Okay, this will be used for this, and then um, protein concentration will be used for this one. Okay. Okay. So now, example here, can you detect? Oh, what is it? How to undo? Okay. From here, do you know what is the unit per mil based on this purification table? Okay, because it gives us here total activity, total activity and total protein. So do you know what is the unit per mil for, activity just unit per mil for this protein? I don't know what is this protein. Okay, so how do we know unit per mil for this protein? Okay, so we have here, the um, total activity, and then we have also the volume here. So in order to get unit per mil, okay, you need to divide, okay, 100,000 unit divided by 1.4 mil. Then you will get every one, every mil, what is the unit? Okay, I repeat, in order to get total activity, okay, if you want to get the total activity, meaning that the activity that you have calculated multiply by the volume, and then you will get the total activity. Okay, so for this case, if you have 100,000 unit, what will be the um, unit per minute? What is it? You can type in the, but I cannot choose this, right? Um, I will go to your chat to see. What's the answer? Give me the answer. What will be the unit per min if you're talking about this? You can type in the chat room. Okay, you have this total activity, and then you have this volume that you have extracted. So what will be your unit per min? What will be your unit per min? From the crude. Okay, just put it in the, okay, Danu says, okay, Danu has given the answer. Others? Okay, so how do you do it? So it is 100,000 divided by 1,400. 100,000 activities divided by 1,400 mil. Then you get unit per mil. So the answer will be 71.43 unit per mil. Okay, same goes to the total protein. So you have got the total protein here. So what will be the milligram per mil? Okay, milligram per mil equal to okay, give me the result for 1 milligram. I mean milligram per mil. What is the unit for I don't want the total protein, but I want the milligram per mil. Okay, so Arbani is it? Okay, so that's correct. So there will be 7.14. This is because 10,000 divided by the volume here. Okay, so now you got it that okay, the total protein is 10,000, and then the activity is total activity is 100,000. Okay, so the specificity here, what will be the specific enzyme specificity? You have the unit divided by milligram of protein. So you have got 10, and then the yield, okay, is based on the total activity divided by total activity. Okay, we do not have the full here, but we can have the full. Okay, so but this table missing the full. So yield meaning that the total activity left after the step. Okay, yield meaning that the total activity left after the purification step. Okay, so if we have the affinity chromatography, so let's say we do not do this part, okay, we don't have this, we don't do this, but we have the affinity, we have the tag just now. So what happened? We will do the affinity chromatography directly. So our purification table will have only the crude result and the affinity chromatography result. Affinity chromatography result. Okay. For example, if we start with this 1,400 ml, okay, we have started with 1,400 ml. Okay, after the affinity chromatography, we end up having only 6 ml. Okay, maybe this is okay, only 6 ml. But the thing that we want to know is the yield. How is it compared to the first round? Okay, how do we get the yield? It's based on this total activity. Okay, the yield is total activity divided by total activity of the step divided by total activity of the crude multiplied by 100. So for this case, why do we get 45%? This is because of the okay, why do we get 45%? It is because of the 45,000 and then divide by 100,000 multiplied by 100. Okay, if we have got the activity 45,000 unit, what will be the unit per mil for this? What do you think unit per mil for this? Give me the answer, unit per mil for the affinity chromatography step. Okay, you can type in the chat room what is the unit per mil affinity chromatography step. What will be the result? Yeah, that's correct. There will be 7,500. Oops. 7,500 unit per mil. Can you imagine? This is really high in activity. Okay, even though you have only 6 mil, but every mil of it contains 7,500 units. if you compare this, okay, if you compare this purified protein, purified enzyme versus the crude. So this is really big gap, right? So you have increased, the activity in every meal. Initially it's just 71, now you have got 7,500 units. So that's why for the 6 meal, you have got only 45% recovery. The yield is 45%. So how do we, okay, for the, okay, maybe you want to know for this, let's just check for the protein, okay? For the protein, what will be the milligram per mil for protein? What will be the milligram per mil of the protein? Okay, check for this. Okay, so you said here 0.5. Yeah, it is 0.5. Okay. If you compare now the milligram of protein, initially it was 7.14. Now you have got 0.5. Okay, it is good because you have low concentration of the protein compared to the initial one. Why? Because the initial one, it mixed up with the impurities. Okay, okay. If you have low concentration of the protein but high concentration, high activity, that means your protein, your purified protein is really pure. So from here, you can calculate the specific activity. So for this case, what will be your specific activity? It will be 15,000 units. Okay? Okay, let's just try. Okay, so if you use 7,500 unit, 7,500 unit per mil divided by 0.5 milligram per mil, you still will get this 15,000 unit. So initially you have only 10 unit, 10 unit of your enzyme in every 1 milligram. Okay. So now in every 1 milligram you have got 15,000. Wow, that's a lot. Okay, just imagine you have this. I'm going to use this red color. So imagine in this container. Okay, inside this container, of course, you will have your protein. For example, this is 1 milligram of protein. Okay, this is 1 milligram. Okay, and then you have the second container, which is after you have purified. Okay, after you have done the purification, and then the new container you have, similar size of container, and then you are talking now with the another 1 milligram. Initially, from this 1 milligram of the crude, is it? I cannot do it. Okay, not from. Okay, how do we go back? Cannot go back. Restore. Cannot restore. Okay, never mind. From this container, you have this. This is 1 gram of protein. Only this, the pure protein. Your target protein. But once you have purified, once you have put it, okay, 1 container, you have only this, which is 10 unit every 1 milligram. After you have done the purification, this is still 1 milligram, but inside this, you have 15,000. So everything here, okay, so everything here They are all your protein. Okay, if you compare the purity, the purity from the start, which is only 10. This is 1 gram. Okay, represent this 1 gram. So the others are impurities. Your protein is only these dots. But once you have purified, you have the specificity up to 15,000. That means all this inside this protein, you have 15,000 units. Okay. So now, in terms of the fold, now we have the fold here, right? So we can prepare the fold. Okay, for the fold of purification, you can check based on the specific activity. Okay, now from this, it will be only one fold. Okay, one fold because 10 divided by 10. Okay, but once you have this purified protein, you have 15,000 unit per milligram. What will be your fold? How many fold do you have? You can type in the group. Okay. So Alia says 1,000. Okay, just type what will be your answer. Okay, Shazwani says 1,500. Others? What will be your fold now? Okay. So the answer will be 1,500. Okay. It is because 15,000 unit per milligram divide by 10, then you get the fold is 1,500. Okay, I would say this is really successful purification in terms of the purities because from 1 you can make it pure up to 1,500. Okay, okay. So the yield is different, right? The yield is because this is what left. Okay, this is what left from the beginning. But in terms of the fold, so in terms of the fold, you have got like, wow, 1,500 fold. Okay. So same goes if you have a few other steps, whatever happened, just refer to you need to divide and compare with the group. How successful is your purification? Okay. For example, if your protein, you cannot go to affinity chromatography immediately, directly, you need to use amino sulfate first. Okay, just use amino sulfate and then check what's left. How much it is increasing. For ion exchange chromatography, how many fold? How many fold it is increasing from the beginning. If you include size exclusion chromatography, then you can see. Okay. So as you increase, the steps in purification, okay, you have introduced a few steps in your purification. That means the loss is also high, and then by the end of the day, you have got lesser yield. Okay. We want to reduce the step if possible, but if you cannot, you need to introduce all these steps. Okay. So you might want to know either it is necessary to start with the amino sulfate first and then ion exchange second and then size exclusion chromatography finally with the affinity. No, it depends. Depends on the whatever evaluation after that. For example, you may want to evaluate. Of course, you will evaluate your protein based on the gel. Okay, you will check on the gel. You will check the purity of your protein based on the gel. Let's see. Either it is suitable to use size exclusion chromatography first, or amino sulfate first, or affinity first, or what. So based on the gel, okay, what does the gel result say, and then plus the nature of the protein. If your protein, I mean, you think it is suitable to use ion exchange, you can use. But because you know now the principle of each technique, you need to decide which one should come first. But normally, most of the time, once you can use affinity chromatography, meaning that it's just one technique. That's why affinity chromatography is a popular method when we say that it can be used, you can use only one technique, one step purification. That's why we use affinity chromatography. It is also considered as one step purification. Okay, so I think that's